Similarly, you can, when people do controlled microscopy and controlled sample preparation, the in TM, when the beam hits this sample, and it is a 300 keV electron beam, so it is a very huge energy, right? And obviously it will heat up. And if that heating up changes the phase constitution of your sample, then what will you do? For that, people do cold stage electron microscopy. They have a thin wire in the sample holder here, and it is connected with liquid nitrogen. Into the liquid nitrogen. Liquid nitrogen temperature is minus 60 degrees Celsius. So it is continuously passing in this range. It is a very thin wire, and that thin wire inside it is hollow, and liquid nitrogen is constantly passing in it, so it keeps the sample cold. The same thing is happening there. As I draw a sample holder like this and we put the sample in, so here it is also keeping the system cold during that process. So if your sample is, anyway people keep liquid nitrogen in the ion beam, old ion beam thinners. The new ones are now not using liquid nitrogen. But all the electron microscopes are kept cool using the liquid nitrogen. But if the sample is also risky, then they have sample holder as well to circulate liquid nitrogen here and avoid the damage due to a transformation due to heat. Similarly, if you are studying live phase transformation in a machine, then you can connect this area. You make a setup, a resistor here, that by changing the temperature, you can take it to high temperatures and you see live phase transformation in the hot stage TM. Cold stage TM, you are keeping it cold by using liquid nitrogen. And hot stage TM, you heat up the material through that system and you see the phase transformation. For example, a monoclinic structure is transforming into a cubic structure, a cubic is transforming into tetragonal structure, the fraction pattern like this is becoming like this. So you see it. So it is in situ, INSITTU, in situ transmission electron microscopy means that you are having the facility in the machine to heat the sample inside it and see the phase transformation. You focus a specific diffraction pattern, then heat it, and you see how the structure changed. And the same happens with the cold one, that at which temperature do you want to look into a sample. And now, in the developed world, there are many laboratories which are doing in situ XRD as well. That phase transformation with temperature is checked. We can control the ion energy, the angle of incidence, as I told you, rotation, how fast the sample is rotating, and temperature of the specimen. So we have all those places. Ion milling and grinding, people use it in the same meaning. Milling means grinding. Ion milling of the most versatile thinning process being used for ceramic composites, multiphasic material, right? Polyphase means that you have polycrystalline material, as we say, or multiphasic material. Polycrystalline means you have multiple crystals inside the sample, but polyphasic means that you have different phases of crystalline material there. Some phases are amorphous, some are crystalline. You can call them polyphasic. And it is also possible that you have the composition of a glass and the same composition of crystals within a material. So the same chemical composition, but some regions are glassy, amorphous, and some are crystalline. And again, they are polyphasic material. So polycrystalline and polyphasic must be distinguished. And alloys and many cross-sectional specimens. Fibers and powders can also be thinned by iron milling. I haven't done it. Here, first the particles of fibers are embedded in epoxy, and the mixture is transferred into a 3 millimeter brass tube for strength. Next, some the tube epoxy mixture into 3 millimeter disc, and finally dimple and iron melt to electron transparency. Did you understand what this means? I have a 3 millimeter tube like this. I mixed epoxy and the powder of the sample. Together, I filled this tube, then I cut it into 3 millimeter discs. The epoxy kept the material hardly, strongly stuck, and you can dimple it, and as well as you can iron thin it, and those powder particles will be thin. Follow that? Yes. Right? Those powder particles will be thin. It became like this. You made a piece, and when you grind it, the epoxy is holding the powder particles, and you are thinning them and dealing it as if it is a self-supporting sample. Yes. Yeah. These are fibers, and there are powders. They are brass tube. They are cut into pieces, and you got that 3 millimeter disc, and this is the way people do it. Cross-sectional specimen. This is the very tedious side of making samples, and a special type of self-supporting disc in which interfaces are studied. Because in TM, you are thinning sample. When you are thinning sample, this means you are removing the surface. Then how can you study the surface? Right? So for this, you make specific arrangements whereby cross-sectioning a sample, interfaces are made parallel to the electron beam. The main cross-sectional samples are semiconductor devices in composite material. The sample can be cut and glued together to produce several layers like a club sandwich. What they mean that you have this material, you have this material, you have this material, you all club together, right? And then take cuts from there. And when you cut it here, you got a cross section here which contains the piece of paper, the piece of metal, the piece of composite, all are there. And you are looking into the interfaces, that how they react with one another. Because people, they are usually studying diffusion. They deposit gold particles, silver particles upon a material. then they heat it, then they take cross sections of those and look into the deposited layer and the bulk of the material and what the infused or diffused ion did with the base matrix. So when you are studying that sort of material, then you need those cross-sectional studies. That how, for example, a sodium ion went into a lithium silicate ion, right? Did it become the part of that structure or it precipitated separately? If it precipitated separately and it had another property for being separate, then that property will be visible. If it interacted with the already present structure and it replaced the lithium ion, then that will make another type of structure there. So what happens because of diffusion? When you want to see them directly, then this cross-sectional sampling is used for that specific applications. And they have shown it here, right? That you club them together, then you put it in the epoxy in that material and you cut those slices and you got the sample from there. You can fix nanofibers on the grid or things like that and polish them or grind them and you can look into them using transmission electron microscopy. And up to now, probably transmission electron microscopy is the most expensive technique as well. So you must think whether you need it or not. If you don't need it, then why waste time and money? Right? So the first thing, you must look for what sort of information do you need. Is it possible through a cheaper technique? If yes, then you are a bad researcher that you are using a TM. If something can be done, right? So when something can be done in a cheap and easy way, the best scientist is that which adopts that easy way. But if something is not possible without TM, then TM is a very, very versatile technique, and never think that it has this limitation, this limitation. We have limitation. Whether we have money, whether we have time, whether we have smartness to devise that particular sort of sample and particular sort of environment. The alternative to self-supporting is this, as I have explained it, right? Crystalline films, carbon films, and there are, in the old days, people used replica methods. Electro polishing, it is an application of electrochemistry, right? It is an application of electrochemistry. First, a 1 square centimeter sheet is cut on it. The ease with which you do many things. For example, you are making a capacitor. A capacitor is a wheel, a circular disc, right? This side has an electrode and this side has an electrode. But how you make electrodes? You put that disc in the sputter coater. For example, the sputter coater is sputtering gold particles onto the sample. It is used in vacuum, and gold particles or atoms are sputtered from the source onto the sample. Then you turn it around, then sputter it. But if this area is coated, then it is short-circuited. So what you do, you first hide this area with a cello tape, right? So the coating on both sides occurs, and when you remove the cello tape, then the short-circuiting is removed. There is no short-circuiting, and you use this material as a capacitor. The same thing they are telling you, that the area you want to thin down, the other is hidden from that electrolyte, and only then window area is thinned down by the electrolyte. And you have selections that which area should be thin and which should not be. And in this way, you can make samples. Ultra microtomy is the next which I didn't use, and the microtomy is used for sectioning biological materials. When you are studying biological material, then ultra microtomy is used with care and practice. The biologists construct a three-dimensional picture of the specimen. The specimens are usually 0.1 millimeter thick for visible light microscopy, and for TM, the slices are less than 100 nanometer thick. The instrument is known as ultramicrotome. We can use it for crystalline materials too. They are probably showing here you the ultramicrotome. This is the specimen, and this is the rough knife specimen moment, thermally advanced arm, feed direction of motion. So they are making thin slices, and then thin slices are fixed onto the grid. This is the typical shape of the grid. If you look into that, the circular, the grid is there, and it gives you thin 3M grid slices, and you can take them to the TM. Biological samples are very difficult because in the conventional microscopy you need very high vacuum, and if a material is a liquid means it's not stable, right? And it is very difficult to do such sample. And nowadays people are using environmental microscopes, which doesn't need vacuum, and for biology they are very useful. But for your purpose, the simplest ways which I mentioned in the start, they are expected from this course, right? You are physical sciences students and you don't need those sorts of complications. But in future, if you happen to have such things, then it is not a difficult thing, right? So you have a little bit knowledge about every aspect of the electron microscope sample preparation. Many materials, ceramics and minerals are mostly prepared by crushing in a clean pestle and mortar, preferably in an inert liquid, stirred ultrasonically and allowed to settle. A drop of this liquid placed on a holy carbon. Holy means which is perforations, holes, right? It is not the park holy. Felt on a grid, evaporate in a dry environment, limit a distribution of particles on the support film. You have fine powders of the sample, you put it in the beaker, acetone is there, shake it well, the denser particle will go down, the lighter particle will come up. You can pick a drop from the top and put it on the grid. After 10 minutes it will be dry, and you can take this to microscope, and if you are fortunate, there will be very fine particles which will be electron transparent, and you can take diffraction patterns and images from there. But अरजान भी इलतनी और ग्रान भी कीमतनी. You will not be able to see the original sequence of crystals which are done in the self-support sample. But if you are fortunate, you will see some particles which are thin, and you can see things. And I have done many samples like that, and I have got enough information from them as well. So it is not completely useless, but as a teacher I will tell you, go through a difficult way, but more reliable and authentic way.